As we begin to collect measurement data on our process that we are seeking to control, we must be aware that the outcome data can fall into two different categories: variables versus attributes. Variables are data that can take any real value. That is, they can be fractions or decimals or even whole numbers. These are continuous random variables. Attributes, on the other hand, are categorical or discrete random variables. The outcomes are measured as either good or bad, or at times we count the number of defects within the output. Attributes are defect-related characteristics. Regardless of the type of distribution that our outcome measurements result in, that's discrete or continuous, our goal is still the same. We want to create SPC charts to help us determine whether or not the process is in control. To help us create the SPC charts, we will invoke the almighty, all-powerful central limit theorem. Hopefully, you recall what the central limit theorem is, etc., from your prior probability and statistics courses. In essence, and I am paraphrasing here, the central limit theorem says that regardless of the underlying population distribution, when we take samples and find the means of those samples, the sample means will approach a normal distribution. That sampling distribution, as it is called, will have a mean designated as x bar bar that is equal to the population mean mu. Additionally, the sampling distribution will have a standard deviation that is equal to the population standard deviation, sigma, divided by the square root of the sample size, n. Please note that x bar bar is the overall mean, not the mean of the sample means. These two numbers can be quite different from one another. And you should verify that the statement I just said is correct with a small example. So again, the power of the central limit theorem says that no matter the underlying population distribution, for example, here we have the beta, normal, or uniform, among any others, the distribution on the sample means will approach a normal distribution. The overall mean, x bar bar, will equal mu. You may also recall that for any normal distribution, 95% of all values fall within plus or minus 2 standard deviations, and 99.73% fall within plus or minus 3 standard deviations. Let's compare what the process distribution of means, or the population distribution, looks like compared to the sampling distribution. Here we have a normal process distribution. It could have been anything, like the beta or uniform distribution we saw in the previous slide. We take samples of size n and calculate the sample mean, the sample statistic that we're interested in. The sampling distribution then begins to form. As the central limit theorem states, this sampling distribution will approach a normal distribution. Notice that its mean, central tendency, is equal to the mean of the process distribution, mu. Notice also that the sampling distribution is higher and tighter than the process distribution. This is because the sampling distribution standard deviation is smaller than the population distribution. Remember, the population standard deviation is divided by the sampling standard, by n, to get the sampling standard deviation. There are 5 steps for creating and using control charts. First, take samples from the population and compute the appropriate sample statistic. A lot of times this will be the mean. 2. Use the sample statistic to calculate the control limits and draw the chart. Third, plot the sample results on the control chart and determine the state of the process. In other words, are we in or out of control? 4. Investigate the possible assignable causes and take any indicated actions. And 5. Continue sampling from the process and reset the control limits when necessary. For this class, we are going to focus on the first 3 steps.